Okay, so hello everyone. So today our group will present a case study about the failure analysis of a conveyor pulley shaft. In this presentation, we will describe the background of the case, explain the observed failure, analyze the stress and the material properties, and finally provide recommendations to prevent similar failures in the future. So now let's start with the case overview. So the failed part was a conveyor pulley shaft made from BS 970 150M 19 steel. It transferred torque from the gearbox to the pulley and also carried part of the motor and the gearbox weight. The system ran at about 79.5 RPM with roughly about 1803 Newton meter of the torque, and the combined motor and gearbox mass produce about 2,300 Newton of vertical load. So even though the material and the basic design were suitable, the shaft broke only 7 days after overhaul, which suggests the failure was caused by something introduced during the reconditioning work. Okay, so now let's discuss about the observed failure. So the shaft fracture at the shoulder near the coupling is a place where that commonly develop a stress concentration. So during the overhaul, the failure radius was machined down to about 0.5 millimeter instead of the specified 4 millimeter, which that greatly increased the local stress. So the fracture surface showed typical signs of fatigue with progressive crack growth and a small final overload area, and also there was evidence of a well-heat affected zone. So overall, the shaft showed the geometry from reconditioning was the main factor that triggered the fatigue failure.
To understand why the shaft failed, we first need to visualize the load it was under. On this slide, you can see the free body diagram, which isolates the shaft and shows all the external forces acting on it. Starting from the left, we have T motor, which represents the driving torque supplied by the gearbox, which is what makes the shaft essentially spin. And then we have FGB, which is the critical downward force, and it represents the combined 230 kilogram weight of the motor and gearbox, which are suspended from the overhung end of the shaft. This will create a significant bending load. Then we have R1, which is the upward reaction force from the first main support bearing located near the gearbox. And we have F belt, which is the downward force from the tension of the conveyor belt pulling on the pulley. And finally, we have R2, which is the second upward reaction force from the other support bearing. And this FPD clearly shows that the shaft isn't just a simple twisting load. It's also subjected to significant bending forces, especially at the overhung end where the gearbox is mounted. Now that we have identified the forces, let's look at the stresses they create and the material's ability to handle them. The shaft was subjected to two main types of stresses: torsional shear stress and bending shear stress from the motor and gearbox weight. Because the shaft is constantly rotating, this bending stress becomes a cyclic load, alternating between a maximum tension and maximum compression with every single revolution. This condition is known as rotating bending, which is a classic cause of fatigue. However, the most critical factor was the severe stress concentration at the shaft shoulder, the sharp corner, which was machined with a radius of only 0.5 millimeters instead of the specified 4 millimeters, acted as a stress multiplier. And this dramatically increased the local stress at that one specific point, and this is where the failure began. So the question is, was the material itself part of the problem? To answer that, we analyzed the mechanical properties from tensile tests performed on the shaft material. And as you can see from the data, the shaft steel had an ultimate tensile strength between 515 and 570 megapascals, and with good ductility, with an elongation between 22 to 28%. The key takeaway here is that the failure was not really caused by the poor material quality. The material itself was sufficiently strong. The steel itself was perfectly adequate for this application. The main culprit for this failure lies in the geometry of the shaft itself. and it will be explained further by my colleagues.
This slide shows the microscopic features of the fractured shaft corner. We can see the weld buildup on the left, with the adjacent heat-affected zone. The crack initiated right at the shaft corner, then propagated across the section. The fracture surfaces clearly illustrate fatigue, with a progressive crack growth zone, and finally, the overload region where the shaft completely separated. This visual evidence supports our conclusion that the failure mechanism was fatigue driven by stress concentration. Looking at the failure sequence, the crack first initiated at the shaft shoulder corner where the fillet radius was too small. With the shaft under cyclic bending, the crack propagated gradually through fatigue. Eventually, the reduced cross-section could no longer sustain the applied torque and bending load. At that point, the shaft failed suddenly by final fracture. The key takeaway is that the root cause was stress concentration at the reconditioned shoulder. To emphasize the root cause, the improper reconditioning process created a very sharp notch. This led to high stress concentration, and combined with the heat affected zone, cracks initiated quickly. Those cracks then propagated progressively under cyclic stresses until the shaft fractured by overload. So the complete chain was improper repair, stress concentration, crack initiation, fatigue crack growth, and final overload fracture. To prevent similar failures, several recommendations are clear. First, always maintain a minimum fillet radius of 4 mm to avoid stress concentration. Second, use proper repair procedures, including compatible filler materials, stress relief heat treatments, and avoiding stainless filler. Third, carry out post-repair inspections such as non-destructive testing and geometry checks. And finally, implement strict quality assurance standards in reconditioning practices to ensure the integrity of critical components like shafts. In conclusion, this shaft failed by fatigue fracture due to stress concentration at the reconditioned shoulder. The sharp fillet radius drastically reduced fatigue life, even though the material was otherwise strong and ductile. The premature failure was caused by a reconditioning error, not material weakness. The lesson is that following design specifications, applying proper repair practices, and thorough inspections are essential to avoid costly and dangerous early failures in rotating machinery.